Hello everybody, welcome to this latest talk. Before I hand over to Chris, if you want to ask questions during the talk, please do them in the chat and I'll raise them with Chris at the end. And if you can keep yourself muted, that would be great. And I'll hand over to Chris, who's a very long-term contributor to ELISA, to talk about Linux and safety systems.
Oh, thanks. So yeah, my presentation today is on Linux and safety systems, challenges and solutions. Some of the content I've already presented in previous workshops, so I just contain a summary. So for those who step in newly, understand at least kind of the thinking I come from and how I look at safety systems, which sometimes differs a little from the mainstream, but that's always a good starting point for interesting debates. So yeah, let's get started. So first of all, what's the challenge, right? So the challenge of a safety context, and we've heard this term in the previous sessions a couple of times, is it focuses around a safety claim. If you have a laptop on your desk and you're not making a safety claim on it, there's no need to make a safety claim. It's not a safety system. And a safety claim is fairly simple, but it kind of bears the challenges in the simplicity. It's something bad will not happen, right? Something bad in the sense of something dangerous that will harm anyone. So really, the safety claim in very simple words expresses that something bad will not happen. And the first kind of key point is that something bad needs to be detailed for the system and the elements of the system. In very general terms, talking about something bad, harmful, it's not that easy. It becomes much easier with consideration of a concrete context. And the safety capability of the system or element is then expressed via safety requirements, and the safety claim is needed by safety standards such as ISO 26262 or IEC 61508. The standards themselves don't contain them, which differs. There are safety standards out there that actually contain safety claims and safety requirements. These two don't. Instead, they provide a process how you can obtain the safety claims, right? So the processes, they are not so much for showing compliance to the process, but part of the process is there to help the person applying the standard actually obtain the safety claims that they need for the system and for the elements of the system. And then what the standards do contain is guidance on how to achieve enough safety integrity. And then the safety integrity says, expresses the amount of care exhibited to substantiate the safety claim, both in the implementation as well as in the evidence and justification. And that is then expressed via the safety integrity level or automotive safety integrity level in the case of the ISO 26262. So it's always important to understand that there is this level of indirection in the standard, because it gets very strange if one tries to apply the guidance from the standard to a system that doesn't have any safety requirements. And I've seen that happen, right? Because there are just things in there. You need process management, you need defined process, and people start cheering and saying, hooray, we have a project that builds ballpoint pens and we have a defined process and we have this and this. And it looks like you can actually claim very high ASILs, right? So it looks easy. But the whole challenge emerges when you then say, okay, what is the technical challenge that emerges, the technical danger that emerges from the system, and how do you mitigate it? So the safety system has a safety capability that originates from a safety claim that is substantiated with a stated degree of care. Another aspect that always emerges in the context of standards is this huge focus on certification. So I kind of just created this very simple diagram. On the left, you can see the standard conformance, and on the lower line, you can see horizontally, you can see is safety achieved. And it's fairly orthogonal. Clearly, if there is no safety need and you don't have compliance to the standard, it's a non-safety system and it's out of scope. The curious thing is that you can have a system that achieves safety and target safety, and it doesn't fully meet the standard. That's why I kind of drew this in a color going from green to yellow, and the standards account for this. That's why they use these terms highly recommended, because there are a number of gray areas where a controlled violation of a integrity clause in the standard is needed or makes sense or is justifiable, and that gray zone is actually needed. And then, as I said earlier, there is this strange world where you can actually achieve conformance to the standard in a very literal way. I don't think the meaning is met, but at least literally sentence by sentence, one somehow can construct an argument that whatever one has built conforms to the standard, but it actually doesn't achieve safety. And I always find that a little concerning because it's confusing. And in some cases, maybe it is even possible to certify something like that. So then someone has something with a certificate, and you say, but what is the actual safety claim on the system, and what has been subjected to the certification? Another way of looking at safety, apart from kind of the famous absence of unreasonable risk statement, is actually it's a safety claim realized with stated safety integrity backed by the credibility of the person making the claim. So anyway, I'm into climbing and other stuff that has a certain level of danger attached to it. And I usually buy my climbing gear from reputable companies, even if you can see kind of gear that looks very similar on the internet sold at cheap prices, but you're saying who is the person manufacturing? And at the end, it's the credibility of the person making the claim, because it's very, very hard in reality to go and re-verify climbing gear or anything you purchase. There's a lot of trust involved. This, in fact, is one of the interesting questions still in the ELISA project, right? Who is actually, when we do make safety claims, who is it who is making it? Is it the Linux Foundation? The Linux Foundation says, no, we're actually not the person making the claim. Is it a natural person, a legal person? It's an interesting topic that one can debate. Or is it the integrator who picks Linux from the web and decides himself and sees a safety claim realized without anyone actually making the claim? So for me, safety is the objective, safety engineering is the approach, conformance and the standards are helpful tools, but they're not the objective. So now when we look at OS basic services, it always makes sense if you look at something that is slightly disconnected from a real system to first of all gain an understanding, what does it actually do? And then from there, it's usually an easier step to say, okay, what are the bad or dangerous things it could do? And then put it into a context or an assumed context and figure out how one could mitigate it. And those are exactly the next 3 slides. So I just took this from Wikipedia. I didn't put that much effort in inventing my own definition. So you have the operating system software, provides common services for computer programs, manages software resources, and manages computer hardware. This shouldn't be something that is contentious. I chose the term workload simply because the term process and task and application and program, they are overloaded so significantly by different communities that I wanted to take a term that was more neutral. But in doing so, I know some people took offense to it. This is not the reason why I chose the term. Just insert your favorite term. How you imagine what the OS executes. If you think the OS executes processes or application software, just put that in there. And now the interesting question is, what are the things that can go bad? So first of all, the OS really gains significance when you start executing multiple workloads. If you just have a single one, it's a quite distorted system. Those systems exist. But in general terms, that there needs to be at least 2. That way you suddenly get the challenge of shared resources, shared processes, shared caches, shared memory management, page tables, shared peripherals, all kind of shared infrastructure. And now you want to use the OS to host coexisting and mixed criticality workloads. And then something bad, there are not that many things that can happen in very general sense. You can get timing corruption. There are tons of papers out there for the last 30 years on how to deal with it, from time-triggered systems, time monitoring, and all the pros and cons. The more dynamic your system is, the higher the schedule jitter gets. So that's moving more towards event-based systems, which limits the time criticality you can achieve and the tightness of the time monitoring. There is tons of research out there. And the other thing that can happen that's bad is data corruption, right? And that's where I kind of see a significant challenge now in the deployment of Linux. Because how can the data corruption occur? First of all, it could be interference between workloads. There are some good solutions out there already from the security space that we can build on. Then there is the interference between the operating system and the workload. So the operating system itself becomes the source of interference. And that, I think, is quite a challenging aspect. That's where the whole world of separation kernels and microkernels lives in trying to address this problem with low overhead. And lastly, we have the controller interfacing to the hardware, and that's where you can get interference indirectly through the operating system managing or having a management problem of shared peripherals, and then you get an interference problem because the shared peripheral then becomes the coupling factor between the workloads. And yeah, so I think that when one starts looking into the kernel, a lot of optimizations that have been done in the kernel kind of trade off how much care or how much protection is put into protecting the OS against the workload versus the speed factor, right? Where Linux really shines. So now one has the problem defined, so there is a significant use case impact, and I think that is a really important aspect to consider when deploying Linux in safety critical systems. This is a slide I created. I showed it 2 years ago in an ARM internal event. We had Linus Torvalds at the table, and we discussed it. L and H are just abstract because there are many variations in between. I just wanted to put 2 stakes into the ground to show how the thinking goes, right? Class L usually, and there are all these exceptions. So don't nail me down on this, but usually the safety complexity is low. Transient faults are not that critical. So the system has a low pass characteristic. Permanent faults are critical. The fault tolerance time is long. You often see humans in the loop, which simplifies the problem significantly. You have systems where end-to-end plausibility checking at an application level is quite feasible. You don't see that much mixed criticality. You might see some coexisting workloads, but it's not the significant requirement on the system, and you're usually looking at lower safety integrities. And then on the class H side, transient faults become critical. Permanent faults are critical. The fault tolerance time is short. There is no human in the loop who can take last second mitigation. End-to-end plausibility checking becomes difficult because the amount of data moved around is so huge that if you have to put end-to-end checking on all the data, it just kills the performance. You're looking at mixed criticality scenarios, and you're usually looking at high safety integrity levels. And here I took some automotive examples, having a significant background in automotive myself. So if you look at the IVI telltales, that's a dashboard that displays critical information. I would put that more in the class L, because you still have the driver who has to look at the dashboard and still has a level of putting comprehension behind it. And if the dashboard goes all blotchy, that's an immediate sign to a person that something is broken in the system. And he's lost the driver has lost the dashboard. Then you have concepts like EGAS, the electronic throttle in between. Gateway can get quite tricky, in particular if you repackage your data packets in the gateway. And then autonomous driving on the class H side. And here on the bottom, again, take this with a grain of salt. This is no science behind it, but usually on applications of class L, you get away without lockstep, and usually on the class H, you start seeing lockstep hardware as a kind of a differentiator. And now, what has been kind of, if you once you've exploited the application level, a lot of focus goes onto the onto the testing. So people try to argue, I achieve safety by construction testing, right? And the idea is that by virtue of extensive testing, for example, the operating system to process type faults cannot occur. And then the argument is that, you know, so much testing has gone into Linux, and couldn't we use that type of testing and to argue that the kernel could not corrupt in any of the workloads running on top of it. And it looks like an easy argument because there's no runtime performance impact. We just take the kernel as we pull it off the web, and there are continuously new methods available and being adopted for Linux. The challenge, in my opinion, is from a safety perspective, there are really some prerequisites that have to be met for the safe by construction testing, and that is in particular kind of one or very limited entry and exit points from the code, restricted use of pointers, no unconditional jumps. These are actually listed in the ISO 262 standard, and the kernel just has a highly nonlinear execution and complex hardware usage patterns. On a multi-core system, it's pretty extensive how the execution jumps back and forth between the hardware, and it gets very difficult to argue that in the interaction between the kernel and the hardware, right, they're not loopholes where fault patterns can slip through. So really, once you start going into this area, you get a state space explosion through the interaction patterns. And I think I'm not saying that the construction testing argument isn't an important one. I think it's a really important one, but by itself, I don't think it can be the sole argumentation. So I looked at, and then I said, okay, just without looking at what do we need, what could we do, right? And basically there are two directions. You can modify the software, you can safety harden the software, and you can exploit special hardware features. So I tried to classify and categorize and put some pros and cons against it. Clearly, if you don't modify the operating system and you don't exploit special hardware features, that is a very, it looks like a very generic solution, but at the end, your complete problem space has to be solved at the application layer. So then it becomes very, very application dependent. That was also what was seen in the SIL to Linux case. Because the safety capability you need is just there through the application. Does this make sense? Yes, in the IVI use case, a lot of the argumentation can be achieved on the application level. So this isn't like it's irrelevant. I think for some use cases, this is a very relevant solution, but it's for that use case and not a general solution. So then you can say, okay, let's try to avoid exploiting special hardware features and look into the OS modification. And here there is always the risk of winding up with a non-standard with a proprietary kernel. You get a performance impact. There's always the question, how do you integrate emerging OS features? Someone has to then translate them to this modified kernel, and the maintenance problem gets ugly. So all the nice features we have in this column, where we say we don't modify the kernel, clearly we're sacrificing them when we start modifying the kernel. And from another aspect would be, what happens if we exploit special hardware features? Well, yes, then we do have to modify the kernel, but if those are special hardware features that are being used by the kernel in any case, because they're attractive for other business use cases, then they become part of the kernel, and really they bleed into this left column of actually not requiring any OS modification for the safety use case, because the kernel is already modified to adopt them. And I've picked 3 features to present here briefly to give an idea of what exists. I think most of you will probably know them, but here's now kind of a serving menu. This is something that is available, it exists. It's called memory tagging extensions. And the idea is, when you obtain a pointer, you also obtain, you set a key for the memory region, and you obtain a key. And when the pointer is used to access the hardware checks whether the key, which now becomes part of the pointer, actually matches the key that has been stored for the memory region. And here you can see if the key stored is 7 and the pointer is used to access a memory region that actually is allocated to key 7, it works. But if you try to access a memory region that has been allocated to key number 4, but you only hold key number 3 yourself, then you're running into trouble, and the hardware can actually detect this. It's a nice feature. There's a whole bunch of papers available from ARM on how long and how many bits do you need for the keys to get a reasonable coverage. And it turns out that with just 4 bits, you can already achieve a very, very good coverage of the system. The difficulty is, again, it comes with a performance penalty. So usually during the development, precise checks are used, and during deployment, an imprecise checking mechanism is used to simply trade off power consumption performance against the effectiveness of the method. Then the next thing the next step has been to say, okay, is it possible to tighten? You know, the memory tagging really creates a very simple compartmentalization across the memory, and could one tighten that? And the next step along the development line is to use realms, and realms enable the execution of the application in a way that the related data is protected from the host, the hardware manufacturer, service supplier, and other software running on the device. So the whole idea and the business case driving this, because these architecture extensions are really, really expensive to develop, is the whole cloud computing, that you can upload your software into the cloud and execute it on a virtual environment, on a cloud hosted hardware, and ensure and be confident that someone isn't spoofing and reading into your data. But clearly this protection also has some support for our safety argumentation. The challenge is that it encapsulates the complete OS kernel with the app, and its compartmentalization at the granularity of a virtual machine. Where it gets challenged is when you start saying, okay, I create lots of very small virtual machine, and I then want to create high speed and efficient communication and interaction across the realms. Then the concept just doesn't work that well. It's really, the idea is really to lock the operating system and the apps in it, and avoid a lot of horizontal communication. So it has some value in the automotive area and for our use case, but I wouldn't consider it to be a silver bullet. And then the last kind of idea that is now in an envisioned one, it's still in the research stage, is a capability-based architecture. So the idea is now to increase the granularity of the compartmentalization in which you can lock your execution into a very fine-grained in address space memory protection. And how it works is it basically defines capabilities that replace pointers for data references, and the capability registers in the tag memory then enforce the strong pointer and control flow integrity. Right? You need compiler support to manage capabilities. You clearly need significant hardware support to manage the capabilities, and the idea would be to define, that's the current thinking, 128-bit capabilities to give an idea of how big do they become, to contain address, bound information, permission information, and so on. The whole thing is a complete trade-off on cost implications, right? Because clearly 128-bit capabilities added to the pointers creates a huge impact on the memory footprint and on the power consumption overhead used, because every time all these gates are triggering as the pointers are being used and are sucking your small battery in your car dry, which you want to use to cover your mileage back home, rather than having it generate dissipation heat by executing these kind of operations on the hardware. And when the platform gets really big, then these factors start becoming apparent. The nice thing is that with virtual memory, the compartment scalability is really limited to tens to hundreds. while if you move to capabilities, you're looking at beyond thousands. And the domain crossing with virtual memory is inter-process communication, while with capabilities is at the level of function calls. So that gives this very nice capability or ability, to avoid using the term we used here, to have frequent domain transitions. Well, the frequent domain transition with hypervised system isn't that effective. So this is the future looking forward, and this might be a 10-year time horizon. It's not a 1-year time horizon until this will, I think, will be at a level where it's going to be seen in hardware that can actually be purchased. But clearly, for our objective to isolate the kernel and to isolate the workloads from the kernel, this would be a really cool feature if we had it available today. So summary is yep, safety, a different definition, a safety claim realized with the safety integrity backed by the credibility of the person making the claim. The two big challenges, process to process, for which we have already security solutions today, and kernel to process, for which we will need emerging hardware capabilities if we want to get a waterproof solution. And then I presented these three hardware architecture extensions as an example of what can be done. The most important thing for all of these architecture extensions is always a driving business case. So I'm in the ELISA group to see if there are things we can pick up, low-hanging fruit that we can include in the architecture. But when it gets to more expensive stuff, we need to be able to show that there is actually a value proposition behind it, because otherwise it just is impossible to get the resources to do this. So that concludes my presentation, and let's see if any questions came in.
Hello.
Yeah. Okay. There's one question. Sorry, just hang on 1 second. There's one question came in on the chat, which I'll still address quickly. Thoughts on safety versus complexity? Absolutely. I mean, on a complex system, safety is harder to evaluate, and I think the biggest challenge is if you have coexisting workloads in a complex system, is all the dependent failure analysis and freedom from interference. The IC still has the beta factor as a quantitative measure to express the coupling. The ISO doesn't have it, but that doesn't mean that the problem doesn't exist. The problem is still there. The ISO standard at the time tried to move away from a numerical target into more of a qualitative argumentation, but the qualitative argumentation needs a solid foundation to argue how you manage the complexity on the system and how the interference doesn't occur. And sorry, the next question. For new hardware architecture, is there any software? So it's for example, the capability-based approach is a complete, tightly intertwined interaction between the software that the compiler generates and the hardware that provides the hardware ability to work and manage capabilities. So yes, there is a tight interaction between the two.
Okay.
Chris, is that an interaction involving the kernel, or is that, you say it's the compiler that implements it? So does that mean it's the kind of interaction between the application and the hardware rather than the kernel and the hardware?
No, it's between the application, the kernel, and the hardware. The hope is that with significant compiler support, it's possible to abstract coding it and managing it from the programmer into the tool. But both the application has to be capability aware and compiled for a capability architecture as well as the kernel. Would I say breaking a complex system into multiple smaller components, improving safety on them is equal to safety on? It depends. Algorithmically speaking, one can have very, very complex systems, like some of the early electric power steering systems. The control algorithm was actually very sophisticated, but the monitoring was really at a very simple, the safety monitoring was at a simple level. Does the torque between the steering wheel sensor and the tie bar exceed a certain threshold? And if it does, then something has gone haywire, and one tries to gracefully degrade the electric power steering and get the control back to the driver, which has its own challenges. So it really depends. I would distinguish between the safety, the complexity of the algorithmic complexity of the system and the safety complexity of the system. If the safety complexity is higher, one breaks into smaller components. If one is able to distribute them across different systems and different entities in the system, that the dependent failure problem is under control, yes, it is a solution at the cost of now fragmenting the solution over a huge number of ECUs. Which brings another problem, right? That's what I always found so curious about safety. You can't really solve the problem in the perfect way. It is always about striking a trade-off between accepting one downside for gaining a benefit. And I think the challenge here is finding the optimal number of entities to break the software into, that the interaction complexity is still manageable, but the execution complexity of each element becomes simpler. Otherwise, the interaction complexity explodes, which is kind of what one sees in the time-triggered architecture world, where the idea was to fragment everything quite nicely and schedule it, but then the scheduling problem becomes horrendous. Okay, I'll hand the control back to Paul.
I think there's one more question from Inga about the realms.
Okay, the questions about the realm management and whether there's open source for that. And to be honest, I don't know. I would have to Google myself if the open source team has made something available. I need to check. I'm honest.
Okay, thank you, Chris.
Yep.
Okay, do we have any more questions for Chris?
Actually, do you know some other automotive use this kind of architecture in some use case? Do you know?
I'm not sure I understood the question. I mean, at the moment, the challenge for automotive generally is that it until about 10 years ago, automotive was still able to drive semiconductor innovations because the business case was significant compared to other semiconductor usages. Now I think it's the automotive industry really trying to pick the technology that is being driven by cloud computing and edge computing in other areas and utilize that in the vehicle. I'm not sure if that is the question you asked, but in 2012, at the time I was still working for Freescale, we presented a slide that showed as of 2015, a single fab would be sufficient to cover the worldwide needs of the automotive industry. And at the time, we didn't expect to see the consequence already by 2020, where we can see the semiconductor squeeze on the car industry is causing huge headaches at the moment. So it all pivots around the business case. If the business case is good enough to invest in architecture, it will be done. And if it isn't, we're going to have to live with some workarounds.
Okay, thank you, Tris.